All right, lesson 12-7. Let's get into it. If you triple the dimensions of the rectangle below, the new rectangle, got two separate questions here. We'll have a perimeter how many times larger than the perimeter of the one that we're looking at right here. And we'll have an area how many times larger than the one that we're looking at right here. Well, I didn't give any dimensions of this rectangle. So how are you going to solve this problem? Should we take a ruler to it and find the dimensions? Okay, well, notice I did not ask for the perimeter or the area of this rectangle, and I didn't ask for the perimeter or the area of the new rectangle either. Okay, I asked how many times bigger will the second rectangle's perimeter be than the first one. I don't have to know how big each one of them is separately to know how much bigger one is than the other. Okay, and that's something that really takes some getting used to. Okay, but this is what algebra is good for. Okay, is to show us that things can be true under all circumstances, no matter what the specifics are. This is what we use variables for. Or if you wanted to, since this problem doesn't provide any actual measures, what you need to learn to do is say to yourself, well, the answer probably doesn't depend on what the given measures are. So I could probably just make some up and answer this question. And you can, and I'm going to do that. It's not the fastest, easiest way to solve this problem, not by a long shot. Okay, but it is instinctively what a lot of students would do. So let's make up some dimensions. All right, let's say this is 2 centimeters high and 5 centimeters wide. Okay, so then the perimeter would be, and I'm going to call this P1, the perimeter of the first rectangle. That would be 2 plus 5 is 7, plus another 2 plus 5 is another 7. That would be 14 centimeters. The area, I'm going to call this A sub 1 for area of the first rectangle. That would be 2 times 5 is 10 centimeters squared. Okay. So now if we triple the dimensions, and dimensions is a word for, it's fairly synonymous with lengths. Okay. Dimension is referring to a length type of measurement only. So if we triple those, we'd have a brand new rectangle, right? And let's make it go 5 centimeters in that direction, and this 5 centimeters here and 5 centimeters in that direction. So it's going to be 15 centimeters wide, and then 2 and 4 and 6 centimeters down. Now, you don't have to draw this picture to scale, right? You could just draw another rectangle that looks the exact same size as this one, but call them 6 and 15, the dimensions that is. All right, and let's figure out now what the new perimeter and the new area are. So perimeter of this second rectangle, 6 plus 15 is 21, plus another 21 going around the right and the top would be 42 centimeters. And the area of this second rectangle would be 6 times 15, which is 90 centimeters. Now, we haven't answered either question yet. Okay. Again, I did not ask what is the perimeter of the second rectangle. I didn't ask what is the area of the second rectangle. I asked, the second rectangle will have a perimeter how many times larger than the original? How many times larger? Okay. Well, the second perimeter is 42 centimeters. The first one was 14 centimeters. So the answer to question A is 42 divided by 14, which is 3 times larger. Okay. Now, that might not surprise anybody. In fact, you might have guessed that before I started doing all of this work, saying to yourself, you're right, what you said earlier, Nortillo, you don't have to do all of this work. It's going to be 3 times larger, and the area is going to be 3 times larger. Except if you're thinking the area is 3 times larger, you're dead wrong about that. Okay, let's calculate this area here. Well, we already did. It's 90 centimeters. How many times larger is 90 than the 10? 90 square centimeters. I'm sorry, that should be square centimeters divided by 10 square centimeters. So the answer is 9 times larger, not 3 times larger. Okay. And because I did draw the second rectangle like to scale, you can see why the area is not 3 times larger, but 9 times larger. I mean, the original rectangle would fit right there inside the second larger rectangle. There's one copy of the original rectangle. Here's another copy of the original rectangle, and a third, and a fourth, and a fifth, and a sixth, and a seventh, and an eighth, and a ninth. There are 9 copies of the original rectangle's area within the new rectangle's area. Okay? So hopefully that convinces you, right? Whereas the perimeter, only 3 times as large. Now, going back to what I said earlier, the dimensions will not affect the final answer here. We could have made up any dimensions, we'd get the same final answer, and I want to show you that with a little bit of algebra. Let's call that first rectangle's dimensions y for the vertical and x for the horizontal. Okay. Now, what would the perimeter of this rectangle be? It would be y plus x plus another y plus another x. That would be 2 x's and 2 y's. What would the area of this rectangle be? It would just be x times y. Now, if you've got a rectangle whose dimensions are 3 times that one, and again, we don't have to draw it to scale, just call the dimensions 3y and 3x. What's the area, or what's the perimeter now? Perimeter is going to be 3y plus 3x plus another 3y, that's 6y's, and another 3x's, that's 6x's. Total perimeter, 6x plus 6y. And can't you see that that is exactly 3 times the first perimeter, right? How about the new area? What's 3x times 3y? It's not 3xy, right? 3 times 3 is 9, and x times y is xy. Well, how does that compare to the original area? It's 9 times the original area. And isn't that an even faster way of doing this problem? But there's still a faster way of doing this problem, in my opinion, or at least a principle that we can apply to make other problems certainly much faster and easier. Honestly, when I demonstrate this last approach to you, which I'm going to continue to push this last approach on all of the problems that we're going to do from here on out. When I first show it to you, you might think to yourself, that's not faster, and it sure is not easier. I don't really understand what you're doing there. And I understand the original way, so that's easier for me, so I'm not going to do it this new way you're trying to get me to understand. Hang with me, because it really will make some problems a lot easier. Okay? So here's the other approach. You know, we could have predicted this answer of a 9 right from the beginning, without drawing, without picturing. We could have predicted that 9. Okay? Because, you know, we multiplied one dimension by 3, and we multiplied the other dimension by 3. And so we end up multiplying the area by this 3 times this 3, or 3 squared, right? If we had multiplied the height by 5 and the base by 5, we would end up multiplying the original area by 5 times 5, or 5 squared. Right? If I gave the same problem, and instead of saying triple the dimensions, I said multiplied all the dimensions by 5, bam, we can just do a quick squaring of the 5 and say, well, the new area is going to be 25 times as big as the original. Any new length, like the perimeter is a length. Keep that in mind. I know a perimeter surrounds an area, but a perimeter measure is technically a length. And so the new perimeter is going to only be 5 times as long. If I wanted to know how one diagonal of the new rectangle compared to a diagonal from the first rectangle, diagonals are measured as lengths, right? I mean, here's a diagonal of that rectangle. You can only measure the length of that thing. So if I made a new rectangle whose dimensions were 10 times as large, 10 times the height, 10 times the width, the diagonal, being a length, is going to also be 10 times as long. But the area would be 100 times as long, 10 squared. Here's the general principle. I'm going to write it 2 ways. The ratio of the areas of 2 similar figures. They must be mathematically similar. I'm not going to write all of those words out here, but that's what you have to understand. Okay? The ratio of the areas of 2 geometrically similar figures. And that's what I get when I multiply all of the dimensions by the same constant number, right? Whether it's a 3 or a 5 or a 10 or even a 1.5. Okay? If you multiply all the dimensions by 1.5, you're going to get a geometric figure which is similar mathematically, geometrically, to the original. Okay? So the ratio of the areas of 2 similar figures can be found by taking the ratio of the lengths of those 2 similar figures and just squaring it. Okay? When we talk about tripling the dimensions of the original rectangle, we're talking about creating a rectangle whose length is 3 times, all the lengths are 3 times the original. The ratio of the 2 lengths is 3 to 1 when you create a new rectangle whose dimensions are 3 times as much as the other. Okay? Here's another way of putting it. We might say the area, wow, where did I get that little splotch from? It's almost like my electronic pencil was working just like a real pen. You know how sometimes you write with ballpoint pens and you get a little splotches when you're writing with ballpoint pens that are not very high quality? Well, even sometimes if you're writing with nicer pens, you sometimes get these splotches. Anyway, I digress. We might say that the area of the second figure being similar to the first figure. And what I've written here is a ratio, right? It's the ratio of area 2 to area 1. That's going to be equal to the ratio of a length in figure 2 to its corresponding length in figure 1 squared. These 2 equations are saying the exact same thing. But what I haven't written down, again, that you got to be aware of, is that these equations are true for similar figures, okay? And also that in these ratios, the lengths in this ratio right here, in particular, the lengths must correspond to each other. Like if I'm taking the base of one rectangle, I got to put that over the base of the other rectangle. If I'm taking the height of one, it's got to be over the height of the other. If you're taking a diagonal, you got to put it over a corresponding diagonal, whatever, okay? For that matter, a perimeter is a length measure. I could substitute L2 over L1 with P2 over P1 because perimeters are lengths. Okay. So if we apply this principle to this problem, okay, the perimeter being a length, how many times larger than the original? Well, just that answer right there, 3. Why did my pen stop writing all of a sudden? 3 times larger. And the area, well, that's going to be 3 squared, 9. Boy, that makes these problems fast. Okay. So let's apply this principle to the second problem here. Your friend buys a piece of property. Okay. She's got to spend $600 for the materials to put a fence completely around it. And she's got to spend $80 for grass seed for the entire property. And then you buy a geometrically similar, okay, that's what's going to enable us to use the principle we've just been talking about, similar piece of property whose dimensions are 3 times, once again, 3 times that of your friends. Now, this problem does not describe the shape of the property at all. You probably picture the piece of property as a nice rectangular plot of land, but it doesn't have to be, right? It could be a piece of property that is quite jagged and has, all kinds of twists and turns in it. But then you buy a similar, geometrically similar, okay? So it's going to be just like the one that your friend brought, but it's going to be 3 times the size. Now, that would be highly unusual for you and somebody else to buy geometrically similar pieces of property that are this odd. So this is kind of a fakey problem. Well, it's fakey if you imagine that one piece of the properties looks like that. If it's a rectangular plot of property, then, well, I think it's not so fakey at all. Okay. So how much are you going to have to spend for the materials to put a fence around your property? Now, we're going to assume that you're going to buy the fence from the same place, that she put her fence around her whole property and you're going to put the fence around your whole property. The problem says that. You're going to buy your fence from the same place. She didn't get a discount. She didn't have to pay any extra. You're going to spend really essentially the same price for the fence. You're going to buy the fence at the same price, but obviously you have to buy a lot more fence than she does. Okay. How much more? How many times more? Right? I'm giving you $600 and I'm asking you this time, how much actual money are you going to have to spend? Okay. I don't want to just know how many times more money. I want to know actually how much money. But if we knew how many times more money, we could just multiply the 600 by that. Okay. Well, now money is not measured in a linear fashion, and money is not measured in an area fashion either. There's no such thing as dollars squared, right? So does that mean when we're talking about dollars that we'd only ever multiply dollars by that number and not by that number squared? So you got to ask yourself, what is this money being spent on? It's being spent on a fence which goes around the property. Here's the fence. It goes from here to there, to there, to there, to there, to there, to there. You're buying for the length of fence. That $600 cost depends on how much length of fence you need to buy, right? So that $600 is in a way a measurement of length. Okay. If you're going to spend money on a fence for a piece of property whose dimensions are 3 times your friend's, then you're going to have to multiply that fence cost by 3. It's going to cost you $1,800 for the fence. Okay. Because that fence is measured as a length, right? That fence goes around the perimeter of the property. But now think about the cost of buying grass seed. What do you do with grass seed? Probably none of you have ever actually done this in your lives, but I don't think this is too much of a stretch of your imagination. Would you sprinkle the grass seed along the edges of the property? No, of course not. You would sprinkle the grass seed over the entire area of the property. So that cost of $80 for the grass seed is really, that dollar cost is really a measurement of area. You see, dollars can depend on the length of something, or they can depend on the area of something. And they can even depend on something completely different from both of those, which we'll get to in the next unit in this course. Okay? And maybe you could imagine what that is, but we'll talk about that later. So that $80 for grass seed really depends on the area. Okay? So if you're buying a piece of property that is 3 times the dimensions of your friends, you have an area which is 9 times your friends. You're going to need to buy 9 times as much grass seed. And so you're going to need to multiply that $80 cost to your friend by 9 to get $720. Look at how little that work is. Actually, I'd like to write it out like this. $80 times 3 squared. $720. Okay? Because I want you to always remember and never forget where that 9 is coming from. Because what if that multiple is not a nice whole number? Okay? What if it's something like, a 3.6 or a 2.7? Okay? I don't expect anyone's going to square 3.6 or 2.7 in their heads. And if you run into a problem like that, I don't want you to get stuck because you can't do that in your head. I mean, reach for a calculator and square the number and know that that's what you got to do to solve this problem. Okay? This is so much faster and easier than if we were not talking about this, I just gave this problem to people in class to work on without me teaching anything about anything. You know what a lot of students would do? They would start making up dimensions of a rectangle for your friend's property, and they might say it's 10 feet by 20 feet, and then they would try to find out the cost of the fence per foot. Then they'd make a new plot of property, 3 times the dimensions of that, 30 feet by 60 feet. They'd find the perimeter of that fence, and then they'd multiply that number of feet by the cost of fence per foot to get the answer. Wow, would that be a lot more work? I mean, it would work, but it's way more work and way more time. Okay? Let's go on to a third problem. Very much like the previous one. Your friend is building a miniature ice skating rink in his backyard. It takes him 4 hours to assemble the wood border around the rink to keep the water and the ice in. Now, what does a hockey rink look like or a skating rink looks like? Well, it's not a nice rectangle. It's not a nice anything. It's a rectangle with these circular ends to it. Okay, 4 hours to frame it with the wood. And then it takes him 1 hour using the garden hose to fill this in with water and freeze it. So you love it and you want to build a similar ice skating rink in your backyard, but you got a lot more room and you've got bigger kids and they need more room to skate. So you're going to build a hockey rink whose dimensions are 2.5 times larger than your friends. Okay. Again, dimensions is a length measure. So this is a length ratio. Okay. Any length of your skating rink over a corresponding length of your friend's skating rink is going to be 2.5 to 1. Okay. So how much time is it going to take you to assemble the wood surrounding your hockey rink? Now, time is measured in this problem in hours. And again, there's no such thing as hours squared. Okay. But there is such a thing as the number of hours it takes you to do something depending on the area of something. Okay? You're filling the whole interior area of this skating rink with water. Okay? So the time it takes you to fill that rink with water depends on the area of that skating rink. Whereas the time it takes you to assemble the wood border going around the perimeter of your hockey rink, that amount of time is a length measurement. Okay? So when you're reading these word problems, if the word problems are giving you things like costs in dollars or times in minutes or hours, you've got to think, okay, what is that time or what is that cost going into? Is it going into something that is essentially measured as a length? Or is it going into something that's measured as an area? Okay. Again, we do not have to invent dimensions for this thing and find actual lengths and find actual areas. That would be so much more work. Okay. The wood is essentially a length measurement. If it took your friend 4 hours, it's going to take you 2.5 times that 4 hours. It's going to take you the 4 hours, but your skating rink has dimensions 2.5 times as much. 4 times 2.5 is 10 hours. See how fast that goes? And again, I will grant you, if we had never talked about this, if I had never taught you anything, most of you probably would get this problem correct, because you would just assume that you should just multiply the first time by 2.5. So you'd get anything correct that had to do with lengths, but you'd get everything wrong that had to do with areas. Okay? The garden hose filling the rink with water, that's you're filling up the whole area. So you got to take your friend's time, which is 1 hour to fill the rink, 1 hour, and you have to multiply that not by 2.5, but by 2.5 squared. That's 1 times 6.25. That's 6.25 hours. Okay. So something I find interesting about the results here is look at your friend's time to assemble the wood, 4 hours, versus his time to fill the rink. 1 hour, only 1 hour. He might say, it barely took me any time at all to fill the rink up once I had it built out of wood. And he might say to you, yeah, the biggest part of this job is actually building the rink with the wood. That's a bear. That takes you a long time. Once you get that done, fill up the rink, it goes quickly. So you're all excited, okay, because it's taking you a really long time to build your rink. And you think, oh man, I'm going to be so glad when I get this last piece of wood joined together, because then it should take me no time at all to fill it with water. And then you get this really bad surprise that it takes you almost 6.5 hours to fill it with water. And then if you've got another buddy who's going to build a rink that is 5 times the size of your friend's, it's going to take your other buddy 4 hours times 5 is 20 hours to assemble the wood. And it's going to take your other buddy 1 hour times 5 squared is 25 hours to fill the rink with water. It's going to take him longer to fill the rink with water than to assemble the boundary. Whereas for your friend, a lot less time to fill the rink with water. And that's because the larger and larger you make this rink, the faster and faster the area grows, right? The perimeter grows at a steady rate, 2.5, whatever the multiple is all the time, grows at a nice steady rate. But the area, suddenly starts growing faster, faster, and it will overtake, perimeter measurements in a hurry. So I think this is actually a useful thing to know, out in the real world sometimes. You don't want to be surprised by these sorts of results. Let's do 2 more problems. And again, here's a problem that students would spend a long time on, and they would get it completely wrong if you didn't learn this bit about the ratios of areas and the ratios of lengths. Okay? Restaurant sells a 12-inch pizza. 12-inch. Is that a length or an area measurement? What is that? Well, you might be thinking it's length. You might be thinking it's area. I mean, pizzas are not just lines. They're not like string, right? You don't buy pizza in string form in only one dimension. You buy pizzas that are either circular or rectangular. They have areas. But is 12 inches an area measurement? It's not, is it? What is it a measure of? I think a lot of you know. It's a measure of the what? Not the area of the pizza. It's the diameter of the pizza. When you order a 12-inch pizza from a restaurant, circular pizza, 12 inches is referring to the diameter. It's not an area measurement. Okay. Same with the 18-inch circular pizza. It's a length measurement. Diameter is a length. Okay. So the second pizza being 18-inch diameter over the first pizza having a 12-inch diameter, that ratio of lengths, length 2 over length 1, that ratio of lengths is 1.5. The second pizza has lengths which are 1.5 times as large as the first pizza. So area of the second pizza over the area of the first pizza needs to be that number squared for, well, that will be the ratio of the areas. Okay. So 1.5 squared is equal to 2.25. I just know that off the top of my head. Okay. So for these two pizzas to be like the same price per amount of pizza, and think about this again, you don't eat strings of pizza, you eat area of pizza. If you bought literally 12 inches of pizza, it would look like a string. I mean, you could eat 1,000,000 inches of pizza, you'd still be hungry because there would be no other dimension to the pizza, right? When you buy pizza, you're really interested in how many square inches of pizza there are, right? That's what you can actually eat, square inches of pizza, okay? So again, if I didn't teach anything about ratios here, what a lot of students ought to find, and this would be their instinct, is they'd want to find out the cost of this pizza per square inch, not per inch, because an inch of pizza means nothing. So then they'd have to calculate the number of square inches in that pizza, find the cost per square inch, calculate the number of square inches in that pizza, find the cost per square inch, and compare the cost per square inch. That's a whole lot of work. Okay? Let's just do this instead. Oh, how come I didn't get an eraser? There we go. Let's just do this instead. Let's just find out that the ratio of lengths of the two pizzas is 1.5. Okay. So if you multiply that first pizza's cost, $14, by not 1.5, by 2.25, because that's the ratio of their areas. Multiply it by 1.5 squared, because again, that cost is not really the cost per inch, right? It's the cost per square inch. That cost is really an area measurement. So you want to multiply that cost not by a length ratio, but by an area ratio. Okay, 14 times 2.25. And I can tell you what that is. It's, well, I'm going to have to do the math real quickly in my head. Let's see, 14 times 2 is 28. And then a quarter of 14 is another 3.5. So that would be $31.50. That's what you should be paying for the second pizza, for the prices of the pizzas to be the same per square inch. But what are you actually being asked to pay for the pizza? Not $31.50. You're being asked to pay only $30. So that's a deal for you. Okay, this $31.50. My notes look better if you look up my notes later. Okay, so pizza 2 is a deal for the customer. Okay, I'm offering a lot more in terms of a verbal description in this video lesson here, whereas in my notes, I have a lot more stuff written out. I think you're better off watching the video than just looking at the notes. Okay. Last problem. If you want to double the area of a circle, by how much must you double, or by how much must you multiply the radius? Do you just double the radius? Again, I'm not giving you any dimensions or measures specifically of any circles. Okay. But let's consider the fact that all circles are going to be mathematically similar to each other, right? I mean, every circle is just an enlargement or a shrunken version of every other circle. Okay. So circles are similar. And so we can apply this idea of ratios to answer this question. We want an area of circle 2 over the area of circle 1 to be 2 to 1. I mean, I could put that over 1 if I want, but 2 over 1 is just a 2, right? Well, going back to what I wrote as our third way of doing problem number 1, okay, right here. This is the key, right? The ratio of two areas is the ratio of lengths squared, or written this way, it's the same thing, okay? So let's go back to this problem. We have the ratio of two areas, okay? We know that the ratio of any two corresponding lengths is going to be, you're going to have to square that. The ratio of areas is equal to the ratio of lengths squared. Or let's write it this way. 2 is equal to the ratio of the two lengths squared. Okay. So what is the ratio of the corresponding lengths? How do you solve this equation for that one variable in there? Take the square root of both sides, right? And so the ratio of the lengths equals the square root of 2. Exactly. This is not an answer that anybody would have come to easily if I were not teaching you about this kind of thing. A lot of people would have guessed, oh, you got to multiply the radius by 2, and that would be wrong. And if I told them that's wrong, then they'd start guessing at other numbers. 1.5, 2.5, 1/2. I don't know. They'd be completely lost. Okay. You'd have to multiply the radius of the original circle by the square root of 2 to get a circle whose area was exactly twice as much. Now, let's check this with some actual numbers. Again, because I didn't provide specific numbers, any numbers should work. Suppose we had the original circle and it had a radius of 5. What's the area of that circle? Area is pi r squared. That's going to be pi times 5 squared, which is 25 pi. So now let's get another circle and multiply this radius by the square root of 2. What is 5 times the square root of 2? If you're thinking, I can't do that without a calculator, Mr. Nortillo, oh my gosh. Don't make me jump through this video and abuse you. It's going to be 5 times the square root of 2. That's what 5 times the square root of 2 is. 5 radical 2, right? So what would the area of this circle be? It would be pi times 5 radical 2 squared, which is pi times 5 radical 2 times 5 radical 2. And all of these numbers are being multiplied together. This is 5 times radical 2 times 5 times radical 2. And again, they're all being multiplied. Then you can change the order of all of these things being multiplied together. And 5 times 5 is 25. And the square root of 2 times the square root of 2 is 2. And 25 times 2 is 50. 50 pi, which is exactly twice as much as the original area. Okay. All right. Good luck on the homework. See you next time.